Chapter 15 was called Toxins and Solutions. It was pretty short, the chapter, as is the review. We looked at what it means for something to be a solution. A solution is a homogeneous mixture. It's where the two components of the mixture are evenly dispersed in one another. Solutions have two parts, the solute and the solvent. The solute is what you are dissolving, and the solvent is what's doing the dissolving. So if you have to think about it, you put the solute in the solvent. For the solutions that we saw, where the solvent was mostly water, it was what we were dissolving into the water was the solute, and the water was the solvent. The idea of conservation of mass also obviously comes into play. If you're making a solution, the mass of solute plus the mass of the water is going to give you the total mass of the solution. But there's a point to which these solvent, the water for example, cannot dissolve any more solute, and that point is called the saturation point. So we looked at the term called a saturated solution, and a saturated solution was one in which the maximum amount of solute was dissolved into the solution. No more would dissolve if you tried to. We looked at concentration for how to measure how much of a solute is in a solution. The idea that the more solute that's dissolved in a given mass of solvent, the more concentrated the solution becomes. And if the solution's colored, we can see it by color. But if it's colorless, like a sugar solution or a salt solution, you can't really tell by the color because it's going to be colorless 100% of the time. But on the molecular level, these diagrams are important to understand that something that's more concentrated has more solute than solvent generally, and then something that's less concentrated or more dilute has more solvent than solute, as shown there. We looked at concentration generally, so the amount of solute per solvent, and there are lots of ways to express concentration. One of those is molarity, and we'll see it. I gave you the formula on the next page. Molarity is just a specific way to represent a concentration. It's one of the many different ways you can represent concentration of a solution. Specifically, the molarity of a solution is represented as the moles of solute that you dissolve over liters of the entire solution. So the units are really specific. So when we look at something that says 5 big M and we read it as molar, like the tooth, this really means there's 5 moles of solute for every liter of solution you have. Now, the concentration alone doesn't tell you how much of the solution you have. You can have 100 milliliters of that solution, or you can have 5,000 milliliters of that solution. The concentration is just giving you a snapshot of the solution and saying in 1 liter of either of those two solutions, you're going to have a certain amount of solute that's going to give you 5 moles per every liter. So if you looked at a little sample of each of these two solutions with the same volume, the number of dots or molecules or particles per volume would be the same. We looked at that with the card activity. Molarity, in terms of doing some mathematical problems, again, the units are really specific. It has to be moles of solute for liters of solution. So if you get a problem that says, for example, calculate the molarity for a solution where you dissolve 50 grams of calcium nitrate in enough water to make 2 liters of solution, you have the 2 liters of solution. That's good, but you don't have moles of solute. You have grams of solute. You have to convert to moles. So now we're using things from previous chapters. We have to use the molar mass of the substance to go from grams to moles. What is the molar mass? Well, we can't tell from the name alone. You need to write the chemical formula. Calcium is +2. Nitrate has a charge of -1. So the formula for calcium nitrate is Ca parentheses NO3 2. Then we go to the periodic table. You look up calcium on the periodic table. You look up nitrogen on the periodic table. You look up oxygen on the periodic table. And you get the molar masses of each of those things. And then you have to multiply the molar mass of each by how many are present. And you should get a molar mass of about 164 grams for every mole, grams per mole. So the 50 grams of calcium nitrate, we're going to convert to moles. I'll use a different color. 164 grams of calcium nitrate for every 1 mole. Grams cancels. We're going to do 50 divided by 164. and you should get 0.30 moles of calcium nitrate. And now that we're not done, that was how the moles of solute. We want to take the moles of solute and place it over the liters of solution, which from the problem they said was 2. So divide that by 2, and you should get 0.15 big M molar as the concentration of the solution. 0.15 moles of solute for each liter of solution. We looked at how ionic compounds like sodium chloride are different than molecular covalent compounds in terms of how they dissolve. And when we did types of bonding in chapter 5, then we looked at it again when we were doing chemical and physical change and how dissolving could be seen as either physical or chemical change. And we brought it up again here because if you had a 0.1 molar solution of sodium chloride and you had 1.0 molar solution of sodium chloride and 1.0 molar solution of sucrose, and you wanted to figure out the concentration of the total particles, there's actually 1 molar of each ion for sodium chloride because it dissociates and breaks up. So if you're starting with 1 mole total, you're going to have 1 mole of each of them. So together you actually have 2 moles of ions. Or the concentration of ions is 2 molar. Where for the sugar, the concentration is still 1.0 molar of particles, and it's molecules there, not ions. So it's different for ionic and covalent substances. The ionic things will break up into ions, and the total concentration of ions is just a multiple of how many ions there are. The last thing that we looked at was actually just making a solution and the steps that are required to make a solution. If you were told that you had to create a solution with a specific volume and concentration, let's say you wanted to make a 500 milliliter solution with a concentration that is, I don't know, I'm going to make up a number, 2 molar. The first thing you would have to do is figure out how much of the solute do you need to mass out, right? So you have the volume and you have the molarity, so we can use that from our equation. I'm converting that to liters because I'm restricted by the molarity formula to use liters, and solve for the numerator, which is the number of moles of solute. How many moles of solute would we need to make a 2 molar solution with the volume of 500 milliliters? 2 times 0.5 gets you 1. So you would need 1 mole of the solute. But then what if you wanted to find mass of the solute? Well, then we're going back to molar mass. So you would find the molar mass of whatever the solute is, convert from moles to grams, and that's where you start. Your first step is after you figure out how many grams of solute you need, you mass out the grams, you place the grams into a volumetric flask, that really precise instrument for measuring one volume only for making solutions. You add some, in this case the solvent is ethanol, you add some of the solvent to the flask to dissolve the solute, right, until it's thoroughly dissolved, and then you add the rest of the solute that you need up to the mark. In this case, it's 500 milliliters. That'll give you exactly 500 milliliters of total solution. Remember, what you don't want to do is add 500 milliliters of solvent and then add the solid, because now you have over 500 milliliters worth of volume. You had 500 milliliters from the solvent plus whatever volume you had from the solid. So it's always important to do the solid first, dissolve it a little bit, and then add the rest of the volume of solvent up to the total volume.